Imagine a star, once mighty and radiant, collapsing in on itself. This is not just any star, it's a massive one, many times the size of our own sun. Over millions of years, it has burned through its nuclear fuel, shining brightly in the cosmos. But now its life is coming to a dramatic end. The core implodes, crushing matter into an incredibly dense sphere. This process happens in a fraction of a second, releasing an immense amount of energy. The outer layers of the star are blasted away in a spectacular supernova explosion, leaving behind a core that is unimaginably dense. This is no ordinary star. This is a neutron star, a cosmic enigma that pushes the boundaries of physics. Neutron stars are incredibly compact, with a mass greater than that of our sun squeezed into a sphere just about 20 kilometers in diameter. Neutron stars are the remnants of stellar explosions, the leftover cores of massive stars that have gone supernova. These remnants are composed almost entirely of neutrons, particles that are usually found in the nuclei of atoms. In the extreme conditions of a neutron star, these neutrons are packed together so tightly that the star's density is almost unimaginable. They are tiny in cosmic terms, only about the size of a city. Imagine compressing the mass of the sun into a sphere the size of Manhattan. The result is a neutron star, with a density so high that a single teaspoon of its material would weigh billions of tons. But don't let their size fool you. These stellar remnants are some of the most extreme and fascinating objects in the universe. Their gravitational fields are incredibly strong, warping space and time around them. The surface gravity of a neutron star is about 2 billion times stronger than Earth's gravity. Neutron stars offer us a glimpse into the most extreme conditions imaginable. The pressures and densities inside a neutron star are so high that they challenge our understanding of physics. The matter inside a neutron star is in a state that we cannot replicate on Earth, conditions so intense that they challenge our understanding of matter itself. The study of neutron stars allows scientists to explore the behavior of matter at nuclear densities, providing insights into the fundamental forces that govern the universe. These cosmic lighthouses, pulsating with energy, hold secrets to the life and death of stars. Some neutron stars, known as pulsars, emit beams of radiation that sweep across the sky like lighthouse beacons. By studying these pulsars, astronomers can learn about the extreme environments in which they exist. They even help us understand the very fabric of space-time. The intense gravitational fields of neutron stars can bend light and affect the passage of time, providing a natural laboratory for testing the predictions of Einstein's theory of general relativity. So, let's embark on a journey to explore these cosmic giants of density and unravel the mysteries they hold. From their formation in the fiery depths of massive stars to their role as cosmic laboratories, neutron stars are a testament to the incredible power and complexity of the universe. Join us as we delve into the fascinating world of neutron stars and uncover the secrets they have to offer. What exactly are neutron stars? Picture this: a star, much more massive than our sun, runs out of fuel. Without the outward pressure from nuclear fusion, gravity takes over. The star collapses violently, its core compressed with unimaginable force. This collapse forces electrons and protons to combine, forming neutrons, hence the name neutron star. These objects are essentially giant atomic nuclei held together by gravity. A neutron star is a city-sized sphere composed almost entirely of neutrons. These neutrons are packed together so tightly that a single teaspoon of neutron star material would weigh billions of tons on Earth. This extreme density creates conditions unlike anything we can replicate in a laboratory. Neutron stars are, therefore, natural laboratories for studying matter under the most extreme conditions. They help us answer fundamental questions about the nature of matter and the forces that govern the universe. The birth of a neutron star is a dramatic event, a cosmic spectacle of unparalleled violence. It is a process that unfolds in the vast, dark reaches of space, where the forces of nature operate on a scale that is almost beyond human comprehension. It begins with a massive star, at least 8 times the mass of our sun, reaching the end of its life. These colossal stars have spent millions of years fusing hydrogen into helium in their cores, a process that releases the energy needed to counteract the force of gravity. However, having exhausted its nuclear fuel, the star can no longer support its own weight. The balance between the outward pressure from nuclear fusion and the inward pull of gravity is lost. The core collapses in on itself, triggering a shock wave that rips through the star's outer layers. This collapse happens in a fraction of a second, but the resulting shock wave is powerful enough to blow the star apart. This explosion, known as a supernova, is one of the most luminous events in the universe. It releases more energy in a few seconds than our sun will emit in its entire 10 billion year lifetime. For a brief moment, the supernova outshines its entire galaxy. The light from the explosion can be seen across vast distances, sometimes even from other galaxies. The explosion scatters the star's outer layers into space, seeding the interstellar medium with heavy elements. These elements, such as carbon, oxygen, and iron, are the building blocks of planets and life itself. At the heart of this cosmic maelstrom, the core continues to collapse. The immense gravitational forces compress the core to an incredible density. It shrinks until it reaches a diameter of only about 20 kilometers. Despite its small size, the core's mass is about 1.4 times that of our sun, making it incredibly dense. This ultra-dense remnant is the newborn neutron star. It is composed almost entirely of neutrons, particles that are packed so tightly together that a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. The supernova forge, through its destructive beauty, leaves behind one of the most fascinating objects in the cosmos. Neutron stars are not only incredibly dense, but also possess strong magnetic fields and can rotate at astonishing speeds, sometimes hundreds of times per second. These remnants are a testament to the incredible forces at play in the universe and the cycle of stellar birth, death, and rebirth. Let's try to grasp the mind-boggling density of a neutron star. Imagine taking Mount Everest, the tallest mountain on Earth, and squeezing it into something the size of a sugar cube. That's roughly the density of a neutron star. A single teaspoon of neutron star material would weigh about 6 billion tons. That's equivalent to the weight of all the cars in the United States combined. This incredible density arises because the atoms themselves are crushed. The electrons are forced into the protons, forming neutrons. These neutrons are then packed together as tightly as the laws of physics allow. The result is an object of almost unimaginable density. It's a density so extreme that it warps the fabric of space-time around it. This warping, as we'll see later, has profound implications for our understanding of gravity. Neutron stars aren't just incredibly dense, they also possess the strongest magnetic fields in the universe. These magnetic fields are so powerful that they can influence their surroundings in ways that are almost unimaginable. These fields are trillions of times stronger than Earth's magnetic field. To give you a sense of scale, Earth's magnetic field is what makes compass needles point north and protects us from solar radiation. To put that in perspective, imagine a force so strong that it could overpower the magnetic field of an entire planet. A neutron star's magnetic field could rip apart atoms from thousands of miles away. This means that the very building blocks of matter would be torn asunder by the sheer force of the magnetic field. If you were to get too close to a neutron star, the consequences would be dire. Its magnetic field would be strong enough to distort the atoms in your body, with fatal consequences. The human body, composed of atoms and molecules, would not stand a chance against such an overwhelming force. These powerful magnetic fields are thought to be a result of the conservation of angular momentum during the star's collapse. When a massive star exhausts its nuclear fuel, its core collapses under gravity. As the core of the star shrinks, it becomes incredibly dense and compact. It spins faster and faster like a figure skater pulling in their arms. This increase in rotational speed is due to the conservation of angular momentum, a fundamental principle of physics. This rapid rotation, coupled with the star's highly conductive material, generates incredibly powerful magnetic fields. The material in the neutron star is so dense and conductive that it amplifies the magnetic field to extreme levels. These magnetic fields are not just static. They are dynamic and can change over time. They can twist and tangle, creating complex magnetic structures. These fields play a crucial role in some of the most energetic phenomena in the universe. They are responsible for the acceleration of particles to near-light speeds and the emission of high-energy radiation. They power the beams of radiation that we observe from pulsars. Pulsars are rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. These beams sweep across space like lighthouse beams, and when they point towards Earth, we detect them as pulses of radiation. The intense X-ray emissions from neutron stars are also a result of their powerful magnetic fields. These emissions can provide valuable information about the properties and behavior of neutron stars. The magnetic fields of neutron stars can also interact with surrounding matter, creating spectacular phenomena such as accretion disks and jets. Accretion disks are formed when matter is pulled towards the neutron star, spiraling inwards and heating up due to friction. This heated matter emits X-rays, which we can observe with telescopes. Jets are narrow streams of particles that are ejected from the poles of the neutron star, traveling at nearly the speed of light. These jets are powered by the magnetic field and can extend for thousands of light years, influencing the interstellar medium. Studying the magnetic fields of neutron stars helps us understand the fundamental processes that govern the universe. It provides insights into the behavior of matter under extreme conditions and the nature of magnetic fields themselves. As we continue to explore the cosmos, neutron stars will remain a key area of research, offering clues to the mysteries of the universe and the forces that shape it.